Okay, so we have another question. This question is about Amdahl's and Gustafson's laws. The multi-core and multiprocessor architectures. There are certain laws that are driving, how much speed up you can get by going to parallel processing instead of single-threaded computation. So I'm going to just go through this example. I'd like to design a multi-core architecture fabricated on a fixed single die area budget of A. And as an architect, you're asked to divide this total area of A into one master core and many slave cores. So we got this master core, and we have the total area is A, and some of them are just reserved to be a single core of length of area S, and the remaining cores are unit square, okay, and there are of course A minus S of them. Okay, so the master core has an S, and of course it's more capable because we assume that the single thread performance of a core scales with the cubic root of its area. We'd like to execute a workload where P fraction of its work is fully parallelizable and the rest is strictly serials. So assume the serial part is on the master core because that would maximize the performance, and parallel part executes on both the master and slave cores. So what we will speed up according to Amdahl's and according to Gustafson's laws. And of course, we would like to compare this to a single core processor of area 1. And so it's going to be a relative performance improvement. So remember, the speed up is going to be given by the time that you spend using a single core. Let's just say it's T1, and the time that you spend by using N cores, let's say. Okay, so in that case, N cores is just this big master core plus A minus S, smaller cores. So that would give us the speed up, and we would like to find that based on Amdahl's approach and Gustafson's approach. Remember, in the Amdahl's approach, the workload is fixed, and in Gustafson's laws, which is much more suitable for cloud systems, and that the workload scales linearly with the number of cores or number of processors available on the cloud. So let's just take the Amdahl's approach, and we have a workload of, let's say, W. So W is the workload, the total workload. And we have P of them is fully parallelizable, and 1 minus P is serial part. So the serial part is that much, which is going to run on, the master core. But of course, we're comparing it to a single core of processor of area 1. So the whole thing, along with the parallel part, is going to run in a processor which is proportional to 1. That's the rate, okay, rate of processor, and this is the total workload. Okay, divided by, of course, this is going to be divided by the time it spent on a multi-core architecture. In the multi-core architecture, there's got to be a strategy, and the strategy is that we run the serial part on the bigger core because it's much faster and compared to the slave nodes, slave cores. So 1 minus P and W is going to be divided by, because it's not a run on the single core, divided by, since I'm comparing, against this unit area square processor, it's going to be divided by cube root of S. The reason is because we are assuming that single thread performance of a core scales with the cubic root of its area. So that's the relative improvement of this master core compared to a unit square processor. Okay, that's why we're dividing this with this number, because there's going to be some speed up with the serial part compared to this unit square processor. Plus, we have this parallel portion of the program of the workload divided by the total number of cores. Well, in this case, since we assume that the the parallel part executes on both the master as well as the slave cores, then we have to include the cube root of s plus a minus s number of slave nodes, but each one of them contributes one, in this case, proportionally speaking. So that is going to be the total number of cores in terms of unit square, and that's going to be what the parallel portion will be executed on. So therefore, finally, all these w's are going away. Therefore, we have on top, we have just 1, right? 1 divided by this number, 1 minus p cube root of s plus p over cube root of s plus a minus s. Okay? This is for Amdahl's law again, as I said before. You can also assume that the entire area can be used as a single core processor instead of a single unit core. In that case, the numerator has to change. Numerator, instead of having 1, you would have to have 1 minus p w plus pw divided by cube root of a. So this, instead of having 1, you're going to have 1 over cube root of a. In that case, because this now, since you're assuming that the entire die is used for a single core, that would basically be more reasonable, because now you're fixing the size of the physical chip size to be fixed, and comparing it to whether you want to use it with a single core as a single core processor, or you want to use it multi-core processor. And it turns out there's going to be some speed up. Of course, it would depend on the parameters of the system, like a, p, and s. Okay, these are the parameters. Similarly, you can also go ahead and do the same thing with Gustafsson laws. In that case, your workload here, this workload would have to scale 1 minus pw plus p, but now you have to scale with number of cores. This could be usually it's in terms of slave nodes, but you can also include the master. So usually it's in terms of slave. So there's an a minus s multiplied by w. So the only thing that changes is the workload's description. In which case the parallel part of the workload now is going to be a function of number of slave nodes, as they can be added, based on the need.